In a calculus course, there are usually three main components. We talk about limits, derivatives, and now the third component of this course, we're going to be talking about antiderivatives or integrals. And first we're going to talk about section 4.1, antiderivatives and indefinite integration. So in this chapter, we're going to be looking at going backwards through the derivative process, backwards through differentiation, and we're going to call that anti-differentiation or finding an antiderivative. So let's define what an antiderivative is. We say the function capital F of x is an antiderivative of f of x if the derivative of that capital F is f of x. Again, this is going backwards through the derivative process. So example 1, find an antiderivative of these three functions, 2x, sine of x, and 1 over x cubed. So let's start with 2x, and again, we're going to be using all of our derivative rules from previous chapters to understand these antiderivatives. So at this moment, we know that 2x is a function that we've seen as a derivative before. It is the derivative of x squared. Using the power rule, bring the 2 down out in front, decrease the power by 1. The derivative of x squared is 2x. So the antiderivative, or an antiderivative of 2x is x squared. Let's do the same thing for sine of x. Think about our derivative rules. We know that the derivative of cosine has to deal with sine. In this case, the derivative is negative sine. But that's not what we want to get. We want to get positive sine. So if we actually look at the derivative of negative cosine instead, we can think about bringing that negative out in front. So the derivative of cosine will be negative sine of x, which is what we want sine of x. So now we know that the derivative of negative cosine is sine. So the antiderivative of sine of x is negative cosine. So to play the game for antiderivatives, it really just comes down to understanding your derivative rules really well. Let's do this one more time. Let's look at the derivative of 1 over x cubed. And it might help to rewrite this as the derivative of, we want to find the antiderivative of that. So we're going to be looking at something that has a derivative that looks like 1 over x cubed or x to the negative 3. In this case, we're going to be thinking about the power rule, and we can think about the derivative of x to the negative 2. Using the power rule, this is going to be negative 2x to the negative 3, which is similar to what we want, but this negative 2 is an issue, so we have to fix that. To get rid of that negative 2, we could instead think about the derivative of negative 1/2 x to the negative 2, which would give us negative 1/2 times the derivative of x to the negative 2, negative 1/2 times negative 2x to the negative 3. And the reason we pick that negative 1/2 is because it cancels out with that negative 2, and we get our x to the negative 3 as desired. So we could say that the antiderivative, or an antiderivative of 1 over x cubed is negative 1/2 x to the negative 2. Or we could write that as negative 1 over 2x squared. Now, this is only the beginning talk of this antiderivative. Going backwards to the derivative rules, we're going to have a more efficient way of dealing with antiderivatives than what we just did right there. So moving on, it's important to know that an antiderivative is not unique. In fact, for any function there are more than one antiderivative. There are actually infinitely many antiderivatives. Let's think about our example 2x. We saw that x squared was an antiderivative, but there's more than that. So let's think about some antiderivatives of this function. We know that x squared is because the derivative of x squared is 2x. But there's much more. We could think about the function x squared plus 1. That's also an antiderivative because the derivative of x squared plus 1 is the derivative of x squared plus the derivative of 1. And the derivative of 1 is 0, so this is just 2x as desired. Think about another one. How about x squared minus 17/5, some weird constant like that. And again, the derivative of that function, since 17/5 is just a constant, would be just 2x. So actually, we could take x squared plus any constant is an antiderivative of 2x. And we're going to label that, instead of x squared plus any constant, we're going to label that x squared plus capital C. And this is, in fact, all the antiderivatives of 2x. There's a quick proof to show that you can't have anything more than that, but it is just x squared plus any constant. We're going to label that plus c. So below, for any function, the set of all antiderivatives is going to be given by that f of x plus c. And what that represents, f of x plus c is not f of x plus one constant, it's plus any constant. So what this actually is this is a set. It's going to be f of x plus little c, where c is a constant. In set notation, c can be any constant. C is a real number, if you want to think about it that way. And this represents all antiderivatives. If that notation is confusing to you, what this really represents is something like f of x plus 0, f of x plus 1, f of x minus 1, f of x plus 1/2, f of x plus pi. It's all constants plus f of x. We're just going to label that using that notation f of x plus c. So moving on, let's look at again the set of all antiderivatives of 2x given by x squared plus c, and those are functions. So x squared plus c is a set or a family, we could think about, of functions. Now let's think about some of those functions. So we could think about when c equals 0, this is just the function x squared. We could draw that function there. But there's a lot more values of c we could pick. We could pick something like c equals 1. And that would correspond to the function x squared plus 1, which is just the function x squared with a vertical translation up 1 unit. We could think about, how about c equals negative 1/2? Doesn't have to be integer values. That corresponds to x squared minus 1/2. Down 1 unit from the x squared, maybe we could have something like, if c equals negative 3, it's going to be x squared minus 3. And we can continue to draw more and more functions. It's just going to be that x squared function moved up and down the y-axis with vertical translation. So let's think about x squared plus c is the function x squared moved up, down, c units. And this is a family of functions that represents all of those functions at the same time. So it's been very wordy how we've been dealing with this so far, thinking about the set of all antiderivatives. So we're going to use some math notation to simplify the process. So instead of saying the set of all antiderivatives of f of x, we're just going to use this notation, this weird squiggle line we're going to call the integral of f of x dx. So again, this is called the integral. And when we take the integral of a function, we are integrating that function, and this is the inverse of differentiation. We'll get into that later in this talk. I think it's important to understand this notation and understand where it comes from and know that this just represents English phrases. Nothing more than that. It is shorthand for saying some lengthy thing like the set of all antiderivatives. So when I have the integral of f of x dx, that is shorthand for some English phrase. We're going to dissect what that phrase means. So the squiggly line, that integral, means the set of all antiderivatives of. The f of x just means the function f of x. We are familiar with that notation. And then the dx represents with respect to x. And again, why are we using this notation? Because it is much easier to write down the integral of f of x dx rather than the set of all antiderivatives of f of x with respect to x. Similarly, the derivative notation is the same kind of thing. Think about the derivative notation d dx of some function. This is just shorthand to say the derivative of, and then f of x. And in that first notation, it also gives us what variable we are differentiating with respect to, in this case, with respect to x. Now, we're not going to see a lot of use of this in Calc 1. In fact, a lot of times Calc 1 students just ignore the dx, but it is a very important part of the integral, and it will, it's a mistake that will catch up to you if you start to ignore that dx. So we're going to say this is an important part of the integral. That is often ignored, and we should not ignore it. All right, so we have our notation. It means something in English. It's not just some magic math writing. It has a purpose. So let's think about some of these things. All of our integrals are going to be with respect to dx, and that's why often this dx can be ignored. We are going to put that in there every time because it is important. So we're going to think about some basic antiderivatives. We're going to call these straightforward antiderivatives. And these are just based on some derivative rules that we already have. So we're thinking about the integral of 0. We're trying to think about what functions have a derivative of 0. And we know that when you have the derivative of any constant is 0. So we could represent any constant with just capital C. So that is going to be our integral of 0 itself. If I have the integral of a constant, well, we could think about that. We know that the derivative of kx is going to give us that k. The derivative of a linear function is just the slope of that linear function. So the rule here is going to be kx plus c. We also have a derivative rule. We know that when you have the derivative of k times a function, you can bring the constant out in front of the derivative. And going backwards to that process, we can do the exact same thing. So if we have a constant in front of the integral, we can bring that constant out in front. And think about k times the integral of f of x dx. For the exact same reason, we know that if I have the derivative plus or minus, or f plus or minus g, we can think about the derivative of the first plus or minus the derivative of the second. And we're going to do the same thing for the integral. This is going to be the integral of f of x dx plus or minus the integral of g of x dx. And then finally, we have this kind of first big rule. We're going to call this the reverse power rule. And this comes from the power rule for derivatives, that when you have the derivative of x to the n, you bring the power down out in front and decrease the power by 1. And we're going to do the opposite of that now. And the opposite of that is we are, instead of multiplying by the power, instead we should think about, instead of subtracting 1 from the power, we are going to add 1. And then instead of multiplying by that power, we are going to divide by that power. So 1 over n plus 1 times x to the n plus 1 plus c. And maybe it's good to think about what is the derivative of this expression. 1 over n plus 1 to the x to the n plus 1. Well, we could take the constant 1 over n plus 1 out in front. And then we can do the power rule on this guy. Bring the power down out in front. Decrease the power by 1. Those n plus 1s cancel out, and we will be left with x to the n. This is going to have our first really, really big rule, this reverse power rule. We're going to use that all the time. All those other rules are very important as well. Past that, we know a bunch of other derivatives that have to deal with trig functions, so we can think about straightforward antiderivatives that deal with trig functions. And really all of these just come down to what are the derivatives of trig functions. So I know that the derivative of sine is positive cosine. So the antiderivative of cosine is positive sine. And then I'm going to add c to that. Add plus c represents plus any constant. We know that the derivative of cosine is negative sine. So the antiderivative of sine, which we talked about before, the integral of sine is going to be negative cosine, and again, plus c. And just keep on going down the list. We know that the derivative of tangent is secant squared. So the integral of secant squared is tangent. And we'll do the last three kind of all in one big thing. We know the derivative of secant is secant tangent. We know the derivative of cotangent is negative cosecant squared. And we know the derivative of cosecant is negative cosecant cotangent, which corresponds to our antiderivatives with a possible negative in there. The integral of secant tangent is going to be secant of x plus c. When you do the integral of cosecant squared, that's going to give us negative cotangent of x plus c. And the integral of cosecant cotangent will give us a negative cosecant of x plus c. All right, so these are all basic antiderivatives that we should know. We're just built from the derivative rules that we should have down. And on the previous page, these are some rules that really help out with a lot of different antiderivatives, especially that reverse power rule we're going to use a lot in this course and in Calc 2 as well. So let's do some examples. Let's find the following integrals. We have the integral of 7x squared. We can use the rule that we can bring out that 7 out in front. So 7 times the integral of x squared dx. And we just need to think about how do we take the integral of x squared, and we're going to again use the reverse power rule. Which is going to become second nature, just like the power rule for derivatives does. This is going to be 7 times increase the power by 1, and we're going to divide or multiply by 1 over that power, so 1/3 x cubed. And don't forget to have the plus c. Now we can think about multiplying that 7, distributing. That's going to give us 7/3 x cubed plus 7c. And this is where we have some weird algebra with this 7c. So again, c is all constants. If you take all constants and you multiply by 7, we still have all constants, which is kind of a weird way of thinking about it. But if we multiply all constants by 7, we still have all constants. Or you can think about if c is a constant and you multiply by 7, it's still just a constant. So we're going to be labeling this not 7c. We're going to say this is 7/3 x cubed plus, if it represents all constants, let's just call that c. And when we're going to be doing this integral, we're not going to go through that process any more than that one time. We're going to usually say that this is 7 times 1/3 x cubed. We're just going to put the plus c on the outside of the parentheses because it's not going to make a difference, which will be 7/3 x cubed plus c. The algebra behind the plus c is a little bit weird, and as you get more practice with it, you get more familiar with how to deal with it. It's important to remember that it's not just one constant, it's all constants. All right, let's do this again. How about the integral of 2 over x to the 4th plus 7? Let's rewrite this first. How about this is going to be 2 times the integral of 1 over x to the 4th dx plus the integral of 7 dx. That's using our rules from a couple pages ago. We can break up the integral over that addition and bring out the 2 in the first one. And then let's actually do one more thing here. How about, instead of calling this 1 over x to the fourth, let's call this x to the negative fourth dx. And now we have two integrals that we know how to do. So the first one here is going to be using the reverse power rule. We're going to increase the power by 1. Negative fourth plus 1 is negative 3, and we're going to divide by that power. And the integral of 7, we're just going to attach an x to it. That's our rule for constants. And what we're going to get in the habit of is we're just going to think about at the end of our integral, whatever it is, we're going to have plus c. We should go through the algebra one more time with that. We have a plus c from the first integral here, plus c for the second integral. And when we go through that process, we're going to have a negative 2/3 x to the negative third plus 2c plus 7x plus c, which will give us, rearranging the terms, negative 2/3 x to the negative third plus 7x, and then what's our constant? 2c plus c, but this represents all constants. So we can think about our answer as just negative 2/3 x to the negative third plus 7x plus some constant c. And we're going to get in the habit of, instead of adding c each time around, what we can do instead is, at this step right here, we can just add c to the end of the integral and go through the algebra. And that's going to be fine because of this algebra with the 7c, or the all constants. One nice thing about antiderivatives is that we can check our answer by taking a derivative. The derivative of negative 2/3 x to the negative third plus 7x, well, we're going to use the power rule, bring the negative 3 down out in front. The negatives cancel out. We're left with 2x to the negative fourth. And the derivative of 7x is 7. I forgot to put the plus c here. Take the derivative of c. You get a plus 0. And that checks out. That's our function that we have at the beginning. Just as it was for derivatives, doing antiderivatives becomes more and more natural the more times you do it. You just need a lot of practice. Though it is definitely the case that antiderivatives are much harder than derivatives, not only because you're going backwards through this rule that you're already familiar with, but because there are many functions that are not easy to find antiderivatives of. And that is a huge portion of what Calc 2 is all about, is going through some techniques to find antiderivatives. One thing we're going to do in this class is focus on this, that we can do algebra or use algebra and trig identities, simplifying things algebraically to make an integral easy to do. So let's look at this example. The integral of square root of x plus 4 over x squared is not a function that we just know what the antiderivative of is, and we don't know how to find it, but we can simplify that to make it into some functions that we can work with using some algebra. So the first thing we can do is we can break this up into the square root of x over x squared plus 4 over x squared dx. We can break up a numerator easily, just not the denominator. So this is easy to understand if you think about how do you combine these two fractions into one. Well, they have the same denominator, so you can just add the numerators together. We're just going backwards through that process. So that makes this easier to do, but then there's one more kind of step to do, and that is simplifying that first fraction. This is x to the 1/2 over x squared, 4 over x squared. And using some rules about exponents, we could write this as x to the -3/2. Subtract the exponents. 1/2 minus 2 is -3/2. And we could write this as 4 times x to the -2, which is a nice thing to do. And this is just going to be using the reverse power rule twice. So let's do that. That's going to be increase the power by 1. -3/2 plus 1 is -1/2. And we are going to divide by that power. Plus 4 times, do the same thing here. Add 1 to that -2 and divide by that new power. Add a plus c at the end. And we can make this look a little bit better. 1 divided by -1/2 is -2 x to the -1/2, and then we're going to have a minus 4 x to the -1 plus c. If you want to write that with some square roots in there, that would be -2 over square root of x minus 4 over x plus c. I'd say both of these are fine answers. Okay, so originally this was not an easy function to deal with, but once we do some algebra, we can then deal with that. Let's do another couple examples with that sort of idea in mind. We can think about how to deal with the integral of x squared plus 1 squared. By itself, that is not an easy thing to do, but we know that we can simplify x squared plus 1 squared as just x squared plus 1 times x squared plus 1, and we can FOIL that or distribute that. And that'll give us x to the 4th plus 2x squared plus 1. And that is an antiderivative that we can find. It's using the reverse power rule 3 times. This will give us increase the power by 1 on the 4th, divide by that power, so 1/5 x to the 5th, plus 2 times, do it for the x squared, so increase the power by 1, and divide by that new power. And the antiderivative of 1 is just going to be 1 times x, and we'll add a c at the end. Similarly, we can do some distributing here for this cubed root of x squared, but it may help to write this first as not cubed root of x squared, but x to the 2/3 power times x minus 3. This will give us, if we distribute that x to the 2/3, it's going to be x to the 2/3 times x is x to the 5/3 power minus 3 times x to the 2/3 power. And now, again, using the reverse power rule, this will give us increase the power of 5/3 by 1. That'll give us 8/3. And we're going to divide by that new power minus 3 times increase the power of 2/3 by 1, 5/3, and divide by that new power plus c. And 1 over 8/3 is the same as 3/8. And when I do 1 over 5/3, that is 3/5. And when you have -3 times that, it's going to be -9/5 x to the 5/3 plus c, which will be our answer there. There are a lot of other things that we could do for algebra to make things easier. Those are just 3 examples. Make sure you can distribute. Make sure you can rewrite square roots and cube roots as just powers of x. We can think about distributing and foiling instead of dealing with something squared. Dealing with fractions, and again, rewriting negative exponents and square roots as exponents are all very common things that we do. All right, so moving on, also, often we're going to be thinking about not just finding all antiderivatives of a function, but finding some particular antiderivative, one antiderivative that fits some kind of criteria. And in that context, we're often going to be thinking about solving some equation here, and this is called a differential equation. And what that is that is an equation with a derivative in it. So this is the derivative dy dx equals 1/2 x to the -1/2. Remember, this is our notation for the derivative. You could also think about this as y prime equals 1/2 x to the -1/2. To solve this differential equation, we can think about finding the antiderivative of that function. So notationally, what's going to happen here is if we have the derivative dy dx is equal to 1/2 x to the -1/2, we can take the integral of both sides with respect to dx. And notationally, what happens here is these dx's here kind of cancel out. We are left with the integral of dy is equal to the integral of 1/2 x to the -1/2 dx. We'll go for the one that we're familiar with as 1/2 x to the -1/2. Using the reverse power rule, this is going to be 1/2 times increase the power by 1 to positive 1/2, and then divide by that power, plus a constant c here. And over on the other side, when you have the integral dy, this is why that dy dx is important, because the integral of this is going to be the integral of 1 times dy, which is just y, plus c. Well, we're going to subtract c on both sides, and that's just going to give us a plus c on the other side. So the solution to this differential equation is y equals 1/2 times 1 over 1/2, which is just x to the 1/2 plus c, or square root of x plus c. Now, we don't need to go through all of that canceling out the dx kind of thing. We're just thinking about if the derivative is 1/2 x to the -1/2, we're using an antiderivative to find that solution. Trying to find a function whose derivative is 1/2 x to the -1/2. So let's write that down. Trying to find function y whose derivative is 1/2 x to the -1/2. And that's using an antiderivative to find that. Now this represents a family of solutions. It's like square root of x, but we're translating that. So we have here square root of x. We can think about here is square root of x plus 1. Here's square root of x plus 2. Here's square root of x minus 3 halves. Let's do one more. How about here's square root of x minus 3. This represents a family of functions, and we are concerned with finding exactly one function oftentimes. We're going to do that on the next page here. So instead of thinking about a family, we can think about instead solving this differential equation with some initial condition. F of some x value equals some y value. That corresponds to one particular solution, one of those curves that we drew, or maybe one that we didn't draw. This is called an initial value problem. And to solve this, we're going to solve that differential equation the same way we did before. So we know that the solution to this is going to be y equals square root of x plus c. Or we can think about this as the antiderivative is f of x, capital F of x equals square root of x plus c. And this initial condition allows us to solve for c. Find which c is going to correspond to our particular solution. So how we're going to do this is f of x equals square root of x plus c. We can instead think about f of 1 instead of f of x. That's going to give us square root of 1 plus c. And we know that that's equal to negative 1. So what's going on here is this f of 1 here corresponds to that f of 1 right there, and the negative 1 right there. I'll rewrite that now. So this is f of 1 square root of 1 plus c is equal to negative 1. Square root of 1 is 1. This is 1 plus c equals negative 1. Solve for c. This is c equals negative 2. So our particular solution that corresponds to this initial condition is capital F of x is going to be square root of x minus 2. Or we're going to think about this as y equals square root of x minus 2. So that's going to be this function right here. Square root of x moved down 2 units. And note that this goes through the point 1, negative 1, which corresponds to the initial condition f of 1 equals negative 1. Again, this is like an x value. This is like a y value. And we're just trying to find the solution that goes through that particular point. If we go back to the original function, we're trying to find the function that goes through that point right there. That would have been one that we didn't draw there, but square root of x minus 2. This is solving the initial value problem will give us one solution instead of all solutions there. Another example of having to solve for c, finding one particular solution, we're going to be thinking about velocity, position, and acceleration. So let's just remember that if we have some position function, we're going to call that p of t for position. The derivative of position is velocity. And the derivative of velocity is acceleration. We'll call A of t. So going backwards through that idea, now we know that if we have the integral, the antiderivative of acceleration is velocity. And we have that the integral of velocity is position. And that plus c is still there. So in this problem, we know that a baseball is thrown upward from a height of 2 meters. So let's just think about what's going on here. We are throwing some baseball, and it starts at 2 meters, and we are throwing it upward at that point. So it is going to go up in the air, reach some peak, and then it's going to go back down and hit the ground. We know that it starts at 2 meters and it has an initial velocity of 10 meters per second. So given that acceleration, given that the acceleration of an object is negative 9.8 meters per second squared, this is the acceleration constant due to gravity on Earth. Everything accelerates at the same rate on Earth. We're going to determine its maximum height. Note that this negative 9.8 meters per second squared, it's negative because when you're throwing the ball up, its acceleration should be decreasing as it's going up. It's going to reach its maximum height, and then it's going to start increasing in the negative direction, getting faster and faster. So we're going to use that information, that A of t is negative 9.8, to determine the maximum height. Let's see how we're going to do that. So we know that if I take the integral of acceleration, here that's going to be the integral of negative 9.8. That's going to give us negative 9.8 times t plus c. We're taking the integral with respect to t, and since it's a constant, we just add a t onto that. It's like a linear function. The problem here is that I need to figure out what is c. So I need one particular solution instead of all possible solutions. The way we're going to do that is we're going to look at this initial velocity. So note that again, this is velocity, but I know that when t is 0, the velocity is 10 meters per second. This is an initial condition. This means t equals 0. The initial velocity is 10 meters per second. And I can use that initial condition to find c. So here I have that v of t is negative 9.8 t plus c. And I know that if I have v of 0, that's going to be equal to 10. And that's going to give me that c is equal to 10, so that means I have velocity is negative 9.8 t plus 10. And what I really want to do is I want to determine the maximum height. So if I need to think about height, I should be thinking about the position function. That's going to correspond to height here. And I need to find the antiderivative of velocity. So position is going to be the antiderivative of velocity, which is the antiderivative of negative 9.8 t plus 10 dt, which will be increase the power by 1. We have our constant out in front, divide by that power, so negative 9.8 divided by 2 t squared plus 10t plus c. In order to find c here, again, we need to ask the question, what is c? And we're going to use another initial condition. In this case, we know that P of 0 is 2 meters. This is another initial condition. It says we start from a height of 2 meters. That's our initial position. So we can find what c is here by saying, again, P of t is negative 9.8 divided by 2. We'll just write that as negative 9.8 divided by 2, t squared plus 10t plus c, and P of 0 is going to be plugging in 0 for t equals 2. That's going to give us c equals 2. So our position function is negative 9.8 divided by 2 t squared plus 10t plus 2. So that is just set up for this problem. Again, what we're trying to do is determine its maximum height. But now we have all the tools we need to do that. We know what the position is, we know what the velocity is, and we know that it's going to reach its maximum height when the velocity is 0. So I'm going to go to a blank page here real quick. We know that we're going to reach the maximum height when the velocity is 0 at a local max of the position function. So we're going to set the velocity function equal to 0, negative 9.8t plus 10, and we're going to solve for t. So negative 9.8t equals negative 10. T is going to be negative 10 divided by negative 9.8, which is going to give us about 1.02. So we know that at t equals 1.02, that's where we're going to reach our maximum height. To find the maximum height, we're going to plug t equals 1.02 into the position function. Again, this is a picture of our position function. To find the y value, we're just going to plug in that t equals 1.02. So we're going to find P of 1.02. It's going to be negative 9.8 divided by 2, 1.02 squared, plus 10 times 1.02 plus 2, which will give us about 7.1 meters. That's our maximum height. Let's look at another problem similar to that. Here, we're not going to be given the initial velocity. We're going to find with what initial velocity can we throw that baseball upward to reach a maximum height of 200 meters. We just found that when the maximum velocity, or the initial velocity was 10 meters per second, we got to a height of 7. We're going to have to throw the ball a lot harder at the beginning to reach a height of 200 meters. So let's figure out what initial velocity do I need to throw that to get 200 meters. Well, again, we're going to start with the fact that v is going to be the integral of acceleration. And we know that acceleration here is negative 9.8 meters per second squared. This will give us, again, negative 9.8 t plus c. And we're going to call v naught our initial velocity. And that is going to be exactly what our c value is going to be here. Think about this as v of 0 equals v naught. And if we plug that into the v of t, we'll get that c equals v naught. It's more just a notation thing right there. And that's what we're trying to find. We're trying to find what is v naught. So again, we're going to have to think about the position function here. So p of t is the integral of velocity. It's going to be the integral of negative 9.8 t plus v naught dt. And just as we did before, this is going to be negative 9.8 divided by 2 t squared plus v naught t. V naught's a constant, so the antiderivative is v naught t plus some c here. We know from the previous problem that the initial position is 2. So we actually do know that p of t is negative 9.8 divided by 2 t squared plus v naught t plus 2. Similar to the last problem, we know there's going to be a maximum height when v equals 0. So we can set v of t, negative 9.8 times t plus v naught, equal to 0. And this will give us that t has to be v naught over 9.8 seconds. So we know that there's going to be a height of 200 at t equals v naught over 9.8. And we can plug that into our position function here to give us p of v naught over 9.8 is going to be negative 9.8 divided by 2 v naught over 9.8 squared plus v naught times v naught over 9.8 plus 2 is going to be equal to 200. And we can solve for v naught here. So doing some algebra on this real quick, this is going to give us a negative v naught squared over 2 times 9.8. There's going to be a 9.8 that cancels in the top and the bottom, and v naught squared, plus a v naught squared over 9.8 squared. Sorry, just over 9.8 equals 198. And I'm going to go to a new page to this real quick. Let's rewrite this. We have negative v naught squared over 2 times 9.8 plus v naught squared over 9.8 equals 198. Let's combine this into one fraction. We can multiply by 2 over 2 here. This will give us negative v naught squared over 2 times 9.8 plus 2 v naught squared over 2 times 9.8 equals 198. Combine that into one fraction, that's going to give us just a v naught squared over 2 times 9.8 equals 198. And now we can solve for v naught. 198 times 2 times 9.8. And v naught is going to be the square root of that mess. Which will be about 62.3 meters per second. Again, with what initial velocity do I need to reach a height of 200 meters? We need to find at what time we reach that height, and we can use that information to find what that initial velocity is going to be. Going back to the original problem here. These last two problems can be difficult. Again, the big key here is that we need to start with acceleration. We can find velocity. We may need to find what plus c is. We can find position from there. And then we just need to play around with those equations to find what is the height going to be or what is the velocity going to be at some certain time. We're going to be dealing with integrals in a lot of different ways. This was an indefinite integral. Let's say that right here. This is an indefinite integral. In the next two sections, we're going to start introducing what is a definite integral. There's a lot of similarities, but there's a very distinct difference that we'll talk about in the next few sections.